Similarly, content is slightly more. It's the same, right? If you look about it here, you can see here is a 1, 2, 3, 4, 5, 6, 7, 8. A positive, A negative, right? Charge neutrality, right? But this part here is a charge neutrality as well, right? This part, right? And then this part is a charge neutrality. Okay? So therefore, once they slightly completely attached together, the upper side of the electron, negative and positive, will be cancelled out, right? There's no electron. Is that okay? Because all the median of this part maintain charge neutrality. But once they separate, right, starts to separate, you could see here the electron flow to here, right? Electron from the bottom side flow to here. So there's a 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 electron flow to here. Because of the 9 electron flow out, so therefore here there's no electron, right? There's no electron, so flow to here. And then to maintain this part, charge neutrality. Okay. And for the single electron mode, is similar to vertical mode. You just no need to consider about the upper side, because the upper side is a separate, always separate. Okay, so you just need to consider about the ground state. Here is the ground state, and in the ground state, right here is the IV curve, is the IV measurement, right? Is IV measurement. So if you look at about here, you could progressively contact, okay? Progressively contact. And then here is maintain charge neutrality, right? Actually, this electrode it is better to draw like this. This is the ground, okay? Because ground should be contact to the electron, coupled, right? Coupled. So in this moment, you could see, because once we fully contact, negative, right? There's no charge, right? No charge. And once they separate, once they separate, there's an electron flow in it, right? Electron flow in here. Right. And they separate at the highest B maximum. right? At the D maxima. So all the electron here flow the highest electron, right? You get the higher peak. You get a higher peak. And then once they come together, together. This is the electron, right? So the electron will flow out, right? Electron flow out. So there's no electron, right? No electron, right? And finally, to here, right? This is D. This is D state, right? D must be. Anyway, you just need to maintain all the carrier need to count the same number, right? All the carrier on the upper side and lower side need to maintain the same number. The upper side of the electron has a 7 charge, positive charge. The lower side should be flow, right? 7 positive charge to layers, right? Doesn't mean flow out 7 negative charge, right? If the upper side is a positive charge, 7 positive charge, it doesn't mean 7 electrons will flow out from the bottom side to the lower side, right? So it should be the same number. Okay, so slightly more, there is also have a freestanding tribal layer, more. Freestanding tribal layer, which is the same, okay? You can see it just separated 2 parts, okay? 2 parts. And then this is similar to the single mode, right? So this electron flow to here, it flow there. So this is just 1 or 2, why we have the 4 mode. This is just 1 or 2 to simulate about the reality of the human being, like take an exercise, like a vehicle, right? Like here is a vehicle train. There's a train on the something like how to say that? This is the orbit, right? 轨道, okay? It's like a vehicle road on the road, okay? So this is just wanted to try to simulate about this thing, the situation, real situation. Okay, single electron mode. Okay, here is a single electron mode. We already discussed about that. So now it's a more particularly application. Okay, this is in our research. We utilize the rice husk materials. Okay, if you look about the rice husk, actually rice husk. Sorry, here it should be realized to 38%, okay, not 95%. Rice husk can be upper consistent. There's an ingredient have a 38% ingredient, silicon dioxide. Okay, silicon dioxide. So if you look about the silicon dioxide in triple series table, right here is the glass, right? Glass is right here. So now you can easily to understand about, if I select tribal electrical materials, glass is quite cheap, right? Glass is quite cheap. But the problem is that glass is only one surface, right? As I show you the video, the Professor only once say why we wanted to select the nanostructure. because the nanostructure on the surface can create high surface volume ratio to friction each other, right? So with a higher surface volume ratio, once the friction each other can be dramatically enhanced, maybe 1,000 or 100 times of the friction layer is only two dimension, right? If two dimension doesn't mean one surface. But if we can create the high surface to volume ratio and then friction each other, it can create dramatically higher output. So that's a very simple idea. Okay, very simple idea. But for the glass, the glass, something like this kind of glass, how to produce the porous structure? Have you think about it? Plus, unless you blow air during formation process, otherwise, glass is hard to generate porous structure, right? But very interesting here is you can see the rice husk. There is a 38% ingredient composition is SiO2, right? But for the rice husk, as we can see, this is an SEM image here. SEM image. The cross-section image looks like it is porous, right? It is porous. But of course, inside of the rice husk, there is a cellulose. Cellulose we call it carbon cellulose, which is organic matter, right? Organic matter. So this organic matter you can release, or you can there's a high mechanical strength, so you can use some acid like sodium hydride, so to release the cellulose. Okay. So finally, release the cellulose, and then you can increase the temperature. The cellulose will be burned out. Okay, that means the CNF will be burned out. Okay, so once the CNF will be burned out, finally remaining porous SiO2. Do you understand? So that means that actually here is the raw material of the rice husk. And then once you burn this rice husk, okay, you will remaining SiO2. Okay, SiO2 because cellulose of organic matter will be burned out. Okay, burned out. So if you look about this natural structure, it is most porous, just like the titanium dioxide. Last chapter 8, chapter 6, we have talked about titanium dioxide, most porous. Most porous is quite good. Why most porous is quite good? Because we wanted to maintain porous. We don't want to maintain particle too small. If a particle too small, that means too dense. Do you understand? Too dense doesn't mean friction each other is hard to each particle content. Do you understand? So still we have to maintain most porous. Most porous is a 介孔系 ，OK， 介孔。Most porous from here to here is nano. Or pore. Porous, it looks like that. There's a lot of the voice. Most porous is just in between nanopores. Still have a voice, but it is easy to make it light to penetrate inside, right? But for the nanopores, you could see they're compact, very dense. Just like a secret key, very dense. Nanopores. Nanopores has a high surface to volume ratio, right? Compared to pores, mesopores. But macropores, you can say macro, M-A-C-R. Macropores is a surface volume ratio too less. Okay. So Now we look at about this is the muscle pulse. Okay, so you might think about, oh, now and so what? Okay, can you show me about what is the difference? Okay, what is the difference? This is the simulation. Okay, tails. The bottom side and the upper side we select PTFE. Teflon. These materials. Teflon. PTFE is also one of them. Can say the Teflon, okay? And we use SiO2 glass. So this is using the console simulation, final element, okay, analysis. As you can see, once two plates, they touch together, suddenly they generate the tribal potential, okay? Tribal potential is about 250, positive and negative, about positive 250 and negative 250. So you can see here, I would say, polarization, right? Polarization. This is also one of the polarization. Oh, sorry, polarization should be 应该往朝下，因为正 positive ID, right? Polarization. Here is, if we look about here, this is positive, this is blue color is negative, yeah, blue color is negative. Red color is positive, right? So red color is SiO2, okay. But now we simulate the surface of the SiO2 is bump to bump. Just looks like that, because you can see SEM image on the surface is like a bump, right? Bump. So you can see on the surface, reaching with PTFE, you can see the tribal potential almost double, right? Positive, negative, here to 680, right? 680. And then if we create a pulse, right? It almost a triple, right? Almost a triple. Once we pulse increase further, you can see almost 4 times compared to the preceding one. You may curious ask me, Professor, so what about, is that large or small? Can I have something to benchmark? Because you told me about 100, 200, so I don't have any idea. Is that higher or lower? Do you understand what I mean? Right? Because the value of the tribal potential, okay, is the relative. It's a relative. So if you now develop a new material systems, and then, for example, you get a number, for example, 10 volt, and then if you do some surface modification and become double, okay, and that's meaningful. That's meaningful, which means that because of your surface modification, so therefore you can increase the material's matter, tribal potential can be doubled. Okay, that means you are doing such a process is good, right? So now for this experiment, before to do this experiment, we just wanted to make sure about the fundamental issue. Okay, whether that porous is meaningful for tribal potential or not, right? This is very important. If porous doesn't increase the tribal potential, why do you want to do such experiment, right? So any of the experiment, you have to use some fundamental theory to support it, right? This is very important. So this is a relative issue. You don't need to care about the value, 1,000, 100, and 10, and there's a how much. You don't need to care about that. The more importantly is about the dramatically increase. Okay, the important is how much that we do such effort, and then this tribal potential indeed increase. All right. So you also can do such experiment or simulation to make sure before to do such experiment. Okay, to do such this is the simulation tells. So we have to do the sample. Okay, using the bottom top side is a PTFE, and then bottom side is a SiO2. Okay, SiO2, which is manufactured from the rice husk. These materials. Okay, these materials. Okay, and then these materials we just coating on the PET substrate, just screen printing on the PET substrate. So you can see on the surface is a pores of SiO2. And then bottom side, upper side is PTFE. So as you can see, they reaching each other, right? It is significant generate output current and voltage. Okay, and the voltage. So as you can see, they can lighting. This is about 158, 56 LED bulb, right? LED bulb. And this is suppose that because the SiO2 we know easy to donate the electron to the PTFE, and PTFE receive the electron, right? So as long as you can prepare both sides, one positive, one negative, you can get the sensor. Okay, so this is a tribal electrical potential that now I wanted to introduce about whether it's possible we can utilize this tribal electricity to do such as LED device. It is quite amazing, right? LED device, you know, the LED device like a MOS effect. Like a CMOS. You have source and drain. You have the source and drain, and then for example, you get the gate side, right? You have the gate side. And you can apply the bias, right? So this source and drain can make the electron or the whole flow from source from one side to another side, right? If we get a bias, right? So you can control on and off switching, right? But now is whether it's possible we can use tribal potential for example, I embedded S to here, D to here, and there is a layer, friction layer. Friction layer, right? This friction layer. If I wanted to make it a positive to here, maybe I can use some contact. For example, you have, right, progressively to touch this friction layer, right? And it will generate a positive side or negative, and it will create the electron flow through the channel. Do you understand what I mean? Right? Later I will show you that. So we call this is the coupling effect. So-called the tribal electricity. If there's a materials has a tribal electricity and also semiconductor, right? And their coupling will be tribotronics. This is the so-called, because as I just mentioned, for the semiconductor, okay, for all the semiconductor, still have the tribal electrical property. Let me show you about tribal series table. Actually, tribal series table is a lot. If we look about this table, this table, okay, let's look at this table. Here is the fur, rabbit fur, you know, rabbit, 兔毛啊, okay, rabbit fur, glass, mica, nylon, wood, and then to around here is the metal, okay, nickel, copper, okay, nickel, copper, and this is silver, gold, and to the right hand side here, negative become negative, which is the plastic. So I would say semiconductor is just around here, for all the semiconductor, okay, semiconductor. All the materials has a tribal electrical property. Just the property is positive or negative. Do you understand what I mean? All the materials, including semiconductor. So you have to carefully look at about, oh, this material is right here or right here. Okay. So if we want to select, for example, titanium dioxide, and then titanium dioxide is right here, you can select polyester. So titanium dioxide will become positive, polyester become negative. Is that okay? So if you select titanium dioxide right here, and you select glass, titanium dioxide become negative, and glass become positive. This is the relative. Okay, relative. You have to be careful with that. Okay. So accordingly, I just wanted to show you about this scenario. So-called now, because we wanted to do some flexible electronics, flexible effect, field effect transistor. It is also has a lot of application like e-skin, something else. So for the traditionally, we know about the gate and source and drain, right? So you have to make in the electron flow or current flow through this way. So we have to put the gate side on here. But now, if we remove the gate side, just remove the gate side, and then remaining, this is only just source and drain, right? And this gate side, we can manipulate using hand or something else, whatever is positive or negative, depends on this is N-type or P-type, right? Because if you have a P-type materials, and the majority is a hole, right? Majority is a hole for the semiconductor. So you have to use the positive charge on the gate side, right? If you're using the N-type of material, majority carrier is the electron, right? So you have to use another. Anyway, let me give you one example to show you. Okay, we call this as the contact electric friction field effect transistor. Okay, so the component is something like that. Very simple. This is not complicated. Very simple. Now we just deposit indium antimony, INSB. INSB is a semiconductor. It's a 3-5 materials. Okay, which is very narrow band gap, right? 0.7 something, right? So, and then we also deposit the source and drain, okay, on the metal. And then there's a PO. PO is a polymer, polystyrene oxide. Okay, polystyrene oxide. Polystyrene oxide is one of the dielectric materials, like the SiO2, right? Because usually, if we want to deposit, you have to deposit, this is metal, right? You have to deposit the dielectric material. In between, as a buffer, right? As a buffer, so we call it the high K material, low K material, right? You have to deposit a dielectric. So now we deposit PO, use the PO because PO is the flexible, right? And of course, SiO2 can be flexible, but PO is more flexible, okay? So we use the PO, and then there's a gate side, okay? So this is the traditional field effect transistor. Traditional field, and this is the N-type. Okay, N-type. So you can look about here, right? There's a VDS. VDS is a voltage source and drain. Right here, VDS. What is the IDS? IDS is right here, right? We can measure the IDS once we apply a gate bias, right? This is the transistor. If you apply the gate bias, you get the measure VDS, right? And also measure the output IDS because of the gate bias, right? Gate bias. Okay, now we just divide about this. Here is from the 0 volt, 0 voltage. Now gate bias is 0, 0, 0, right? So you can see as I apply from 0 part to the 5 to the 10 volt, okay? From 0 to 10. Here, from 0 to 10, you can see IDS is increased, right? Do you see that? IDS increased. But if I apply negative charge, IDS, right, reduce, right? So that means that this is governed by N-type behavior, right? N-type behavior. Just divide this is the N-type behavior. So this ISB is the N-type behavior, semiconductor behavior. Again, okay, you can see 0 is right here, 0, 0, 0 volt, 0 gate bias is right here. Once I apply a positive bias, you can see the IDS increase as increased VDS, right? Once I apply negative bias, you will reduce, right? We get the IDS reduced. So this is N-type behavior. If this trend is opposite, then this semiconductor is P-type. Okay, this is very common, okay, very general, all right? This behavior just wanted to justify my device is an N-type behavior. All right, now, I wanted to remove the gate bias, right? Using a tribal friction, okay? So I select, okay, 2 mode, okay, 2 mode. The first mode is using the Teflon, okay? Teflon. And then here you can see is the PO surface, right? So PO PO, the tribal electrical potential, tribal electricity PO is positioned around here. It's pointing east right here. Teflon is the highest negative charge, Teflon, right? And PO it will be lowest, right? So PO become positive, right? In contrast to the Teflon. Teflon become negative in contrast to PO. Is that okay? Oh, okay. So this is A mode. Another mode, okay? I select. Here is alumina. Bottom side, top side is alumina. Bottom side is still PO, right? So PO, as I mentioned, just close to the negative, right? But for the alumina, become more positive, right? So based on the PO, alumina it will be positive. Based on alumina, PO is negative, right? So this is two mode, okay, two mode. Just wanted to justify, can I use a negative or positive charge? I remove the gate side, whether this tribal potential can perceive similar to the IV curve like a field effect transistor. Do you understand what I mean? So now you can regrade. There is no gate side. No gate side. Okay, no this side. Okay, just using friction. And whether the curve can be shown or not. Okay? So this is also the simulation. Okay, tell us. Okay, this is also a simulation. As I mentioned, okay, PO is positive. Teflon is more negative, right? Because PO contrast carry positive, right? So as you can see here, it's more negative, right? More negative charge. Blue color is negative charge, but the PO is a positive charge, right? So you can see once PO versus Teflon, PO versus Teflon will be blue color, will be right here, right? Will be right here. This is blue color. And then red color, alumina, and PO will be right here, right? So what is the, let's look at about this. This is tell us that the tribal electrical potential versus the distance difference. You can look at about, if I increase the distance, the tribal potential will be increased, right? No matter what for this type or this type, same situation. Is that okay? So this simulation tells us we can use the distance modulation and then to manipulate the tribal potential. So-called, if I progressively contact, okay, or progressively there, and then this tribal potential will be modulated. Once this has been justified, and that means the experiment might be able to do it. So you can look at about this A mode. Okay, remember about this. A mode is PTFE, right? PTFE on the top side, bottom side is PO. Okay. So if you look about this, you apply the force, and then contact, fully contact. So therefore, there's it's a charge neutrality, right? And here is the drain side, here is the source side. Once it separates the distance, okay, you can see, once I separate the distance, this is the zero, okay, zero. I measure the radius, the curve looks like that. And then once I increase the distance, you can see the IDS is progressively increase. You may curiously ask, Professor, why this distance is not similar? Because device sometimes is not stable. So So this is just wanted to show you about the scientific. So no, do not challenge you about, because sometimes the trend is good, is right. Okay, the trend is right. So you can see, okay, for example, 20 distance, you can see, okay, radius increase for 40, 60, and 80. So that means you can see, oh, here, as I increase the distance, and then you can see, because the distance increased, and here is positive, right? So therefore, the electron must flow in to the INSB. This is INSB there, right? So INSB will flow in the electron. So therefore, it creates a pink color. This pink color we call the enhanced mode. That means INSB inside of the carrier being enhanced, right? Because the electron flow in, right? So that's why you get the IDS as you increase the distance. IDS increase, IDS increase, IDS increase, because the electron flow in, right? Once you get the masma D, right? You get the masma D, you can see all the electron maintain the charge neutrality with the whole of the PEO. So you get almost the saturate, okay, almost the saturate, almost the saturate. So once you reduce the distance, okay, reduce the distance, you can see because this side and this side will become contact each other. So therefore, the enhanced mode inside of the INSB, the free electron must be flow out, right? So the electron flow out, that means no more of the carrier maintained in the INSB, right? So the current will drop. Is that okay? The current will drop. Okay, so this is one mode that if we using the Teflon, okay, as the contact ratio, and you can see the IDS is increased. So now the problem is, okay, so what about the next? Is there any application about this? Yeah. For example, your iPad, your iPhone, your cell phone, you can touch it, right? And then you can browse it. So that means if you can maintain the distance, and then the ID current will be different, right? That means the distance modulation difference will generate the difference current, right? So therefore, this can be used as a device, just like a switch, similar to FET device, right? So okay, in contrast, another mode, me mode. Me mode now we replace PTFE, right? Using alumina substrate. Alumina become positive, right? Alumina is more positive, but now PO will become negative because alumina are more positive than PO. So PO become negative. Okay? So once you touch together, so there is no electron, right? No electron. So that means you still maintain the blue color. This blue color is right here, similar to this curve, right? Similar to this curve. Next step, you can see once you increase the distance, the IDS drop, right? The IDS drop. Why the IDS drop? This is because of, you can see, because this is a positive, this become negative, right? So in order to maintain this part charge neutrality, so therefore the electron must flow out. So therefore inside of the INSB should be carried by positive, right? So carried by positive because the N type of materials, if we carry by positive charge, that means the mobility will be, I would say, the ID, the current will be low, right? So therefore the current will be dropped, right? Because inside is positive. That means cancel the majority carrier of the electron. Do you understand? You can think about, for example, the pristine INSB. The carry concentration is 10 times, for example, N type, okay, N type, INSB. Carry concentration. Then I have, for example, it's just any number, 10 times 5, okay, 10 times 5. Number of 50, okay, for cm cubic, right? For cm cubic. And then because electron flow out, right? So the carrier concentration will be dropped, right? Is that okay? Carrier concentration will be dropped. So the carrier concentration being dropped, the IDS will be reduced, right? Once you increase the distance. Once you increase the more higher distance, right? All the electron and hole, the inside of the INSV maintain more positive charge. This is one to cancel out PEO, right? So you can see you get the lower IDS, right? You get lower IDS. So now the pink color just image. Pink color looks like a depletion node. You can scenario, 想象, image pink color is the depletion node. This depletion node thicker in INSV or thinner in INSV, right? This depletion node right here is the positive charge, right? So you can see once the distance increases, the depletion node will progressively increase. That's why IDS will be reduced, right? Here, depletion node is become thicker, the thickest, right? So you get the lowest IDS. Once you close again, this depletion node becomes thinner, right? Thinner, and then IDS will be increased. Okay? So this is another mode that we use the anomina to replace the PTFE. PTFE is negative, anomina is positive. So that we can use a positive side or the negative side to justify, right? To justify the behavior. Okay? Like the N-type or P-type behavior. Do you understand? Okay? So for the A mode, we using the Teflon. It's still inside, we call the pink color is enhanced mode. Enhance what? Enhance carrier concentration. Right? Enhance carrier concentration. Because once the electron flow in, you can see the pink color thicker. Inside this pink color is negative charge. Do you understand? So that means the INSV carrier will be, concentration will be increase. That's why once the distance separate, you will get the IDS increase. Okay? So this is we using the two separation mode, and then to easy to demonstration that this is possible to using FET device. We call it tribotronics. Okay, so-called if the materials is a simultaneous has two effects. One is a triple electron effect, another one is semiconductor effect. So you should be able to do the couple device. All right, couple device, something like that. So this is just take a summary. Okay, take a summary. As you can see, all of the piezoelectric nanogenerator, triple electric nanogenerator is a different mechanism. Okay, but inside has a JD. JD is a current output. For the piezoelectric, it's because of the displacement current being generated. Right? This displacement current is D. Right? It's a D. This D including epsilon zero and then E electrical field. Right? And the polarization. This polarization is because of the electrical field created, right? And then this is also suddenly polarization, okay? Polarization of the piezoelectrical materials, right? Piezoelectrical materials. And also, for the triboelectric, okay, triboelectric, because inside could be gap, just only air, right? So you still have two effects. This is a Maxwell, epsilon L, E, and P, and still we have a PS. This PS is a triboelectricity, okay? So this triboelectricity, you can see, they still have a polarization, right? Because this is positive, this is negative, right? Polarization is to be this way. But right here, inside is the piezoelectric materials, and you still find the polarization, right? Because of the non-central symmetry, right? This is created by non-central symmetry. So for the summary, I would say both triboelectric materials and piezoelectric materials both have created the polarization. But one of the polarization from the piezoelectric material is relative to the non-central symmetry, which non-central symmetry, once we apply the strain, and it will create a dipole moment, okay? And this dipole moment can create as electricity. For the triboelectric materials, right, the polarization is relative. The positive charge is separate and negative charge is separate, suddenly separate, and create a polarization. Okay, create. And this polarization will, as a function of the time difference, so-called partial P over partial P. Okay. Because this polarization will be as a function of the time. That means the difference time will get a different polarization, right? Because the distance is different. Okay. So anyway, this is just to take a summary for you guys to understand about that. Okay. Okay, we have 5:30. Okay, let's take a break.